TG. This is lesson 6.1 for Algebra 2. Today we're going to be talking about roots and radical expressions. And I think we'll start with something you've already experienced, finding square roots of different values. So in front of you, you see 4 problems that I'd like to have you try at this time. The square root of 49, the square root of 0.09, the square root of x to the 6, and the square root of 16/25. So take time at this moment and see if you can evaluate each one of these without a calculator. Okay, welcome back. As you can see, the first 4 I completed them with you. Hopefully you got the same answers as I did. But as you can see, we're looking at square roots. Now, something you may or may not realize, but every square root has an index. It's a 2. It's there. We don't list it there, but it's assumed to be there. This is called the radical sign. It's a square root symbol. And what it means when we calculate the square root of 49, we're asking what number to the second power is 49. And as you can see, I can rewrite the square root of 49 as 7 squared, which becomes 7. With the square root of 0.09, that's a perfect square decimal. It's 0.3 squared, which is 0.3. Now with this third one, it's a little different. To rewrite x to the 6th power, we'd have to rewrite that as x to the 3rd squared. Remember, with our properties of exponents, we multiply exponents, and that's still x to the 6th. That gives us x to the 3rd. We apply an absolute value to that to ensure that it's positive. And one little set of rules you can use is on at the bottom of your notes here. It says right here that any problem that has an even index and an odd exponent outside the radical sign requires an absolute value. And that's what we have here. If you go back to the top here, we have an even index 2, and then when we bring it out front, it turns into an odd exponent. And the reason for this is we want it to be positive. And of course, if we put a negative in here, it could be a negative answer. So the absolute value keeps it positive. And then the perfect square fraction is simply the square root of 4 squared over 5 squared, which is 4/5. Now, the next set of problems that we have are simplifying square roots again. What we're going to ask you to do is I'm going to hit pause and see how far you can go with the next 3. So give it your best shot, and then when you're done, it will give you I will have the answers worked out for you. Okay, welcome back. As you can see, I've worked out the next 3 square roots of simplifying. As you can see, the answer to the first one is simply 5 square root of 3. 5 times the square root of 3. When I broke it down, I thought of a perfect square that goes into 75, and that perfect square is 25. So of course, it's 25 times 3 is still 75. And then I broke 25 down as 5 squared, which becomes 5. And then the 3 stays underneath the square root sign. I did that with the second example here also, the square root of 48x to the 10th. I wrote this as 16 times 3. That's how I broke the 48 down. 16 became 4 squared. 3 stayed as 3. And then I rewrote x to the 10th as x to the 5th squared. When I square root 4 squared, I get 4. When I square root x to the 5th squared, I get x to the 5th. I am required to use absolute values because it is an even index and an odd exponent out front. And then we end up with a 3 underneath the square root sign. And then the last one, very similar process, as you can see. This is 9 times 5, which is 45. Square root of 9 became 3. X to the 4th squared is x to the 8th times x is x to the 9th. X to the 4th squared becomes x to the 4th. I do not need absolute value signs there. And then we end up with 5x left underneath the square root sign. So hopefully that went well for you. Now let's branch out. We'll get into maybe radicals that you have not worked with before. These have indexes of 3. And anytime you're dealing with a radical that doesn't have an index of 2, they will list the index in front of you. Square roots will not always put the index there. They may or may not. But it's 2. It's assumed to be there. Cubed roots will have to put a 3 there. Now when we do these, it's a very similar process. The first step is to figure out, okay, what number to the 3rd power is 3? And I think you can think through this. You end up with 8 can be rewritten as 2 to the 3rd power. And anytime we take the 3rd root of something to the 3rd power, it's just that something value, which is in this case 2. So our answer becomes 2. Now, the second one is a little unique. Up to this point in time, we're used to seeing a negative under the radical sign as being a no solution type example or using imaginary numbers. This one has a real solution because we can take the cubed root of a negative. Here's how. We would rewrite this as the cubed root of -4 cubed. And I've changed nothing here in my problem. And that just becomes a -4. -4 cubed does work out to be a -64. And then our last example here to rewrite this, remember we're dealing with perfect cubes here, so I'm going to rewrite this radical as x to the 4th power cubed. That gets me to x to the 12th, and I still have a couple x's here, so x squared. If I multiply x to the 4th cubed times x squared, I still get x to the 14th. The reason I did this because is now I know that the cubed root of x to the 4th cubed is just x to the 4th times the cubed root of x squared, and that becomes your final answer. So it's very similar to square roots. You just have to basically think in terms of cube roots. Okay, I'm going to stop there and let Pearson take over for the rest of it. They're going to show you a couple more examples with 4th roots and 5th roots, and they'll give you their interpretation of this lesson. Thanks for watching, and good luck.